Okay. So let's see what about the radiation of an on Monday, if you remember, we had discussed to some detail the electric dipole radiation, and we stated what the magnetic dipole radiation looks like. Now today let's try to derive the general expression for the radiation of a localized source. So if you remember, when we were studying electrostatics and also magnetostatics, what we had done was we just made this expansion, the electric field, we made the monopole term, there was the dipole term. In the case of the magnetic fields, we only have this magnetic dipole term, and we didn't study the higher order terms. Well, basically we can do exactly the same thing here. So if you start with the scalar potential of an arbitrary charge distribution, this was given by d cubed r prime, the rho at the point r prime at the time t minus r prime over c divided by r minus r prime. Now the first approximation we will do will be, the system we are thinking about is, here is our charge distribution, here rho is different than 0, J is possibly different than 0. We can have some current, some charge distribution. They can be doing some arbitrary motion. And the size of this system is, let's say, D. This is the size. In a sense, they can be contained in a volume, in a spherical volume of diameter d, and we are basically trying to observe the electric and magnetic fields at a faraway distance. Basically, the behavior of the electric and magnetic fields at a faraway distance is what tells us whether the system is radiating or not. So this is at a point, let's say this distance is r, so d is much, much smaller than r. And keep in mind that r prime, if this is our origin, r prime is less than or equal to d, basically. So r prime is much less than r. Now, if this is the case, then r minus r prime, we had already seen that this we can write as r times r minus r hat dot r prime over, no, this is it, r minus r hat dot r prime. If you look at your notes from the on Monday, we had this expression for r minus r prime, and 1 over r minus r prime becomes 1 over r1 plus r hat dot r prime over r. Now, within this approximation, the phi, r, and t become, here I also have the 1 over 4 pi epsilon 0. This is 1 over 4 pi epsilon 0, d cubed r prime, rho of r, t minus r over c, plus r hat dot r prime over c, divided by r times 1 plus r hat dot r prime over r. Plus, there are other corrections. Now, the next thing we will do is we will basically expand this rho around t minus r over c, using this as a small parameter. This is r prime. This is rho of r prime t minus r over c. This is the first term in the expansion, plus rho dot at r prime t minus r over c times r hat dot r prime over c, plus terms of the order of rho double dot r hat dot r prime over c squared and higher order derivatives. We will ignore those. Well, what this basically means is if you just take rho to be some harmonic, some charge density that changes harmonically, rho double dot is nothing but omega squared rho. So what we are basically assuming is omega d over c is much, much less than 1. Because that rho dot is omega squared. So this number over here, this has magnitude 1, this has magnitude less than d, let's say. This is c, the cosine is something less than 1. So if this condition is satisfied, those terms are automatically negligible. And this tells me that d should be less than c over omega. Which is, sorry, don't forget your question, which is lambda. So basically, if you remember our discussion of the electric dipole moment, we didn't really talk about this approximation, but somehow that was implicit in our derivation. We didn't explicitly state it. This approximation just tells me that I can ignore these higher order terms. This tells me that the size of my system should be less than the wavelength of the radiation emitted. Yes? Well, you see, if rho is 0, phi is 0. Well, there's no charges, there's no potential. We will see. You see, this is not the only part. This is the scalar potential, there's also the vector potential. So maybe if rho is 0, at every time, at every point, even in that case, there will be radiation. That will be magnetic dipole radiation. That will be because of the vector potential. Now, let's see, this phi of r and t then becomes 1 over 4 pi epsilon 0, d cubed r prime, rho of r prime, t minus r over c, divided by r. Well, let me write it explicitly first. Well, from now on, I will just drop these arguments. Just keep in mind that rho is everything is in the integrand is, every function is at the position r prime. They are evaluated at the time t minus r over c. So this is rho plus rho dot r hat dot r prime over c, 1 plus r hat dot r prime over r times 1 over r. 1 over 4 pi epsilon 0, d cubed r prime. I have the 1 over r. You see, I'm integrating over r prime. This is just r. d cubed r prime of rho at r prime at the time t minus r over c plus rho dot r hat dot r prime over c plus rho r hat r prime over r. Which is equal to 1 over 4 pi epsilon 0. Now Now the first term is just the volume integral of the charge density. It is the total charge. Well, the total charge at the time t minus r over c. But I'm kind of assuming that I have in mind this isolated system. All the charges are there, currents running in the system, but no current is leaving my system. So I'm just looking at a localized charge distribution with a localized current distribution. So Q is independent of time. The total charge is conserved. The charge at the time t minus r over c is the initial charge, whatever charge the system has. So it's just, this integral is Q, I have the 1 over r. Well, since the total charge of my system is not changing, it's just the total charge kind of behaves like in electrostatics. This is nothing but the electrostatic potential. Then we have plus r hat over c r squared integral of d cubed r prime rho r prime. Times the time derivative. You see, it is this term over here. The time derivative, I just took it out of the integral. This r hat vector is a constant vector. C is a constant. I just take them out of my integration. And I have 1 over r, not r squared. Now, is this integral familiar to you? It's the electric dipole moment. No, it's the charge density multiplied by its distance. It's the electric dipole moment. So this is nothing but P at the time t minus r over c, at an earlier time. And now we have this last term. Plus 1 over r squared r hat dot, I will just write P. Let me just rewrite them. 1 over 4 pi epsilon 0 q over r. This is the monopole term of the potential. Then I have the dipole term plus 1 over 4 pi epsilon 0 r hat dot p divided by r squared. This is just the dipole term. Again, keep in mind that this is at the time t minus r over c. But then I have this additional term over here. Plus 1 over 4 pi epsilon 0 c r hat dot p dot divided by r. This is kind of the new term due to the electrodynamics. So this term we already expected in a sense. So if there is a dipole moment, this is the dipole potential. If the dipole is constant, this is the term we have. The only difference is that if the dipole is changing, since the signal travels with the speed c, it arrives at my observation point at the time t minus r over c. It takes r over c amount of time to reach my signal at my point. So the dipole potential is determined by the dipole moment at an earlier time, at the time t minus r over c. But now we have this additional term. Now this additional term will be interesting, will be more relevant for us because you see it depends on the inverse power of r. It is the 1 over r term, just like the monopole term. That is why this will become the radiation field we have. Also keep in mind that it's inversely proportional to the speed of light. So that is why this is in general small, but nevertheless, since it is the radiation field, it can travel a huge distance. Whereas the field due to this one will not be traveling a huge, the electromagnetic energy related with this term will not be able to travel much. It will be stuck close to the source. This will go to infinity.
Hocam şurada şey dedik ya işte T eksi R bölü S ve R bölü C süre öncesini görüyoruz bir sinyal. Hani şu anki sinyali göremiyor muyuz? Her zaman R bölü C kadar öncesini mi görüyoruz?
Yes. Depends. Well, you say if you are looking at the stars, it can make years. Of course, if the dipole is at your position, and if I'm over here, of course not much. Unless it is oscillating very fast.
Hocam o zaman bu yıldızların şimdiki pozisyonlarını nasıl ölçüyor?
We cannot. We can predict. We just look at how they were moving, I don't know how many years ago, and if we want, we can extrapolate it.
Hani bu kızılötesi kameralar, teleskoplar falan kullanıyorlar.
They are measuring the stars at years ago. For example, we are saying that, okay, the universe is 14 billion years old. So we are seeing stars that were in the universe 14 billion years ago. We don't know what happened to them now. We are not measuring or observing stars at their current position.
Sadece tahminde bulunuyoruz şu an.
Well, we are not even, why should we do that anyway? We can if you want to, but why do we want that?
Diyelim ki mesela Güneş'e en yakın olan yıldıza gitmeye çalışacağız işte uzaydaki gibi. Diyelim ki o da bir 600 yıl uzak.
4 years. No, it's just 4 years.
4 şey.
Alpha Centauri. Alpha Proxima, I think, the closest one.
O zaman onun yerini kesin olarak söyleyebiliriz aslında.
Yeah, I mean, in 4 years it will not move that much. It doesn't have a large relative velocity relative to the sun. So it's more or less where we see it. More or less.
O zaman bu hani galaksiler falan gözlemliyoruz ya. Onların yeri de aslında bilinmiyor yani.
Well, we know their positions many years ago.
Ama şu anki yerleri bilmiyoruz.
No. Who knows? Maybe they just exploded. They might not even exist, some of them. Okay, so this is phi. The scalar potential. Now we can do the same treatment with the vector potential also. The vector potential it is basically mu0 over 4 pi d cubed r prime j of r prime at t minus r prime over c divided by r minus r prime. Or let's say if you just look at one of the components, now this basically is exactly the same as our expression for the scalar potential. The only difference is that instead of 1 over epsilon 0, we have mu0. So we can basically directly use the previous result. So this will be equal to mu0 over 4 pi. Well, Q is nothing but the volume integral of this one. D cubed r prime jr r prime t minus r over c divided by r. That is the first term. Well, the second term becomes plus mu0 over 4 pi r hat over r squared d cubed r prime What we called P was just Ji, whatever we had inside the integral, times R prime. This is the magnetic dipole. And then we have the last one, plus mu 0 over 4 pi c, r hat over r, d by dt, d cubed r prime, ji r prime t minus r over c, r prime. This is our vector potential, the I component of the vector potential. Well, we know that this is 0. The first term will be 0.
Manyetik çarpı.
There is no magnetic monopole. Well, it won't be 0, by the way. You see, this is time dependent. Let's see, will it be 0 or not? Let's look at them term by term. D cubed r prime ji r prime t minus r over c. What is this? What do we know? We know the equation of state. Okay, you see, if you remember our electrostatic discussions, we could use this identity in magnetostatics. And the way we proved it was, if you just look at this thing, this is del over del xj of jj xi, which is del jj by del xj xi plus jj derivative of xi with respect to xj. So the divergence of jxi was equal to the divergence of j times xi plus j times Kronecker delta ij. Divergence of jxi is equal to the divergence of j xi plus ji. So instead of j, in magnetostatics, this was 0. So instead of ji, we could use this term, but the integral of this term over a volume is 0 because we can write this as a surface integral. And on the surface, j is 0. But now we are not in magnetostatics. This term is not 0. What is this term?
0.
Yeah, minus. So this is equal to minus del rho by del t times xi, of course. So ji is the divergence of j times xi plus del rho by del t multiplied with xi. This is our new identity. So let's look at the first integral. This is equal to d cubed r prime divergence of j xi plus del rho by del t times xi. Well, again, this term is 0 because if I take the if I just convert this to a surface integral, the current at the surface at my surface is 0 at all times. So the first integral is 0, but I still have the second integral. And the second integral, I can take the time derivative out of the integral, r prime rho xi, but this is nothing but pi, the electric dipole moment. So you see now in electrodynamics, A you see this was our vector potential at the top. The first term just gives us at the point r at the time t is mu 0 over 4 pi 1 over r times dp by dt. At the point r at the time t, no, not at the point, at the time t minus r over c. This is the first term.
Yani hareket ettiği zaman monopol varmışken dipol magnetik dipol varmışken değil mi daha?
Yes, it tells me that a changing electric dipole also creates a vector potential. Not just a magnetic dipole, but a changing electric dipole also creates a magnetic vector potential. Well, that makes sense. Just remember the example of an electric dipole radiation we had. We had this rod, and the charges was going up and down. This system doesn't have a magnetic dipole moment.
Magnetic monopol sahip olduğumuz anlamına gelmiyor.
No, this is not magnetic monopole. This is due to the changes of the electric dipole. Look, again, let's go back to that example. We had this rod which just carried current up and down. There is a current, so there is a vector potential. There is no magnetic dipole moment. There is only a changing electric dipole moment, and it is what is creating this vector potential.
Yani hocam bundan dolayı mı biz hani yüklerin hareketinden dolayı manyetik alan oluşuyor?
You say here, not because of this, but this is because moving charges create a magnetic field. If the dipole is changing with time, the only way that it can happen is that the charges are moving around. So if there is a changing dipole, there are moving charges, and hence there is a vector potential created. It doesn't require a magnetic dipole moment. Now let's look at the other terms. Well, you see, this is the only term that, this is the term that creates this electric dipole radiation. But let's try to relate the other term to the magnetic dipole moment also. Okay? Now, what is the definition of our magnetic dipole moment? Do you remember? Let's say at the time t, this will be jr prime t cross. Well, I don't have a wire. I have an arbitrary current running.
dV.
Let's look at the example that is more familiar to you. We have a loop. Okay, so here there is some current running I. So this is my DL. That wire will contribute to the magnetic dipole moment by an amount, let's say this is dA. Its contribution will be I times dA. Let's say dA is in which direction? Let's just define the dA vector out of the screen. Basically mu times dA. The contribution from that segment. Now this is R. This is the R vector. R cross dL is nothing but dA. Do you agree? Now you see here we have a triangle. The area of this triangle, which is this dA number, is R times this height over 2. So that's why I have 1 over 2. If you look at the magnitude, it already contains the R, while the height is nothing but dL times sine of this angle. But sine of that angle is also the sine of this angle over there. dL times the sine of the angle between R and dL. So this number and this, they have the same units. And they have the same direction. So instead of this, the contribution to the total magnetic dipole moment, I can just say it's 1 over 2 R cross I dL. Or if I convert it to a volume charge density, this will be 1 over 2 R cross J d cubed R. Because dL is in the direction of J. So here I have a factor of 1 over 2. Here I have the R prime cross J. This is my expression of the magnetic dipole moment of an arbitrary current density. Do you agree now? Now this expression is valid for any current density, not necessarily one lying on a plane carried by a wire. So you see, the magnetic dipole moment is nothing but the integral of the product of some components of the current plus some component of the position, just like those expressions over there. Not an arbitrary product. There is a cross product over there, so we will need to do a bit more work to be able to write that integral in the second line, the integral of Ji r prime in terms of this magnetic dipole moment. Now first let me write the I component of the magnetic dipole moment. And let me multiply this I component by epsilon I jk. Now why do I multiply it? You will see in a moment. Just keep with me. So this will be equal to 1 over 2 d cubed r prime epsilon I jk. Well, the I component of this expression of the cross product will be epsilon I L m x prime L j m. This is equal to 1 over 2 d cubed r prime. That product is Kronecker delta jl, Kronecker delta km, minus Kronecker delta jm, Kronecker delta kl, xl prime jm, 1 over 2 d cubed r prime, xj jk, minus x k jj. Well, in the case of magnetostatics, we could still do one more trick to actually show that these two terms contribute the same. And if you remember that the trick we had done, d cubed r prime xk jj, we had written it as d cubed r prime xk, the divergence of j xj, which was equal to d cubed r prime, the divergence of xk j xj minus d cubed r prime j xj scalar product with the gradient of xk. And the first term, this term, we could just convert it to a surface integral. The surface integral was 0, and the gradient of xk is just nothing but k hat. So we are just taking the k component of this thing. So this is equal to minus d cubed r prime jk xj. Well, this was, of course, in magnetostatics. Now we have a correction to here. Now, are you following? Now, you see, once I have this identity, the contribution of this one and this one, they will be the same. So I can just ignore this one, multiply this by 2. So that 2 cancels this one. So the product of xj, well, these are primed coordinates, by the way. They are inside the integral. Multiply product of xj prime multiply with jk. Just I can write it in terms of the magnetic dipole moment. Look at that second line over there. That is what I have. If you look at the components of that thing, it's just j times r, the j times x prime. And I was kind of done expressing everything in terms of the magnetic dipole moment. This is what we did in magnetostatics. Now let's correct this one, correct this result we have over here. d cubed r prime xk jj. This is equal to d cubed r prime xk, divergence of j xj. It is this term just like we had in magnetostatics, this one, but now we have this additional contribution. You see, we have this additional term. Derivative of rho by dt plus del rho by del t xj. Now with the first term, I can do just like as I did before. So that term just gives me minus d cubed r prime jk xj plus d by dt d cubed r prime rho xj prime xk prime. Well, these are just higher order terms. So these will be the quadrupole moments. So I can just safely ignore them. And I just recover what I had also in magnetostatics. I'm left with this one. This result is actually correct up to higher order corrections in the size of my charge distribution, also in electrodynamics. So that's the main result. So let's go back to our full vector potential now. You see, we already had this term plus additional terms. Exactly, nothing changes. So we can still use our magnetostatic result. for that product. Oh, hold on. Let me just do one more thing. So we have this term. No, okay. A. This is the first term. Now the second term is mu 0 over 4 pi xj over r squared. It is 1 over, there's no 1 over 2 epsilon I j k mu k. You see, the result we have now is that epsilon I j k mu I, this is equal to xj prime jk d cubed r prime. This is the result we have. We use in magnetostatics. Now we had seen that it's also valid in electrodynamics up to the terms that we are ignoring. You see, if you look at that term over there, I'm looking at the j component, sorry, that's the cube. I'm looking at the j component of r hat. So inside the integral, I have ji x prime k. So I have the ji, I is the last index. Now inside the integral, I have ji. Here, k is the last index of the epsilon. X prime has the index j. So j is the second index. And mu has the same index as the first index of the Levi-Civita, k. So that is the second term in my vector in the expression of my vector potential. And plus the last term is mu 0 over 4 pi c. Well, basically it's the same thing, except then the coefficient and the time derivative. So xj over r cubed epsilon kji mu k dot. Well, this is the I component. And now if you write it in terms of the vectors, A vector at the time rt is mu 0 over 4 pi 1 over r p dot at the time t minus r over c plus mu cross r, well, mu 0 over 4 pi mu at the time t minus r over c cross r divided by r cubed plus mu 0 over 4 pi c mu dot cross r over r squared. Okay, so this is basically our final expression. And again, you see, in the case of magnetostatics, we only have this term. No additional term. Now, when we have electrodynamics, there's additional contributions to this term. You see, this term behaves like 1 over r squared in the vector potential. This is not really something we want. This term, which is responsible for the electric dipole radiation, behaves like 1 over r, and this is due to the change in the electric dipole. So since if the electric dipole is changing, it means there are moving charges around, and if there are moving charges around, it will contribute to the vector potential. And this is due to the changes in the magnetic dipole moment, because if magnetic dipole moment is changing, for example, if you just imagine a magnetic dipole as a loop, for example, it can be that the current is changing or the orientation is changing. That means some additional currents in the loop, and hence there is this additional term. This additional term is also 1 over r. And this term is the term that is responsible for the magnetic dipole radiation. Now, basically, these are the expressions that we had already studied on Monday. The electric dipole moment radiation had this term, vector potential, and the vector potential had this form. The scalar potential had the form that we had derived before. Had that form on the first line. That's what we had. This is the vector potential, so the final expressions for the electric and magnetic fields in the radiation zone is basically the same. So let me just rewrite them. So we have the electric field is given by, in the radiation zone, that is the faraway point, is just mu 0 p double dot t, let me use the notation of the book, sine theta over r theta hat b. This is if mu is equal to mu dot where both 0. And B radiation is mu 0 p double dot T0 divided by 4 pi C of course, in this expression, we are assuming that P is in the Z direction. Well, I don't know if you need to have both of them 0 at the same time, but mu dot definitely needs to be 0. Probably you don't need this. Okay, part of your homework. We already have derived the expression for the vector potential and also for the scalar potential when there is a magnetic dipole moment and when there is an electric dipole moment that is changing in time. So I just ask you to derive the corresponding electric and radiation fields. And when mu dot is equal to 0, you should basically, mu double dot is equal to 0, basically, you should get these radiation fields. Yes, both of them are non-zero. Well, in fact, it's just the second derivative that we need in the radiation zone. Yes. No, not the, you see, you will take the derivatives of the vector potential, this one, and the scalar potential, that one. Keep in mind that B is the curl of A, and E is equal to minus the gradient of phi minus del A by del T. Keep only the terms proportional to 1 over r. So this will simplify your life. And if you have a 1 over r squared term, just throw it away.
Vektör field'in türevini alalım ki.
B field is defined as the curl of the vector potential.
Zamana göre türevini almamıza gerek yok.
No. Just take the curl. Curl is a derivative also.
Ama şuradan zamana göre türevini istiyor ya. New double dot.
You see, when you are taking the curl of the vector potential, you see, when you are taking the curl of the vector potential, you need to take the derivative with respect to position. Position appears here, but it also appears in the time argument of the dipole moment and the electric dipole moment and also the magnetic dipole moment. The derivative with these electric and dipole moments that we define over here, they depend only on time. So the derivative with respect to r will involve the derivative of mu with respect to time, with respect to t minus r over c, and then the derivative of t minus r over c with respect to the components of r. So that will bring you additional time derivatives of the dipole moments. Okay, let's give a break now, and then we will continue with recitation.
Hocam bir şu yukarı yaksanız da